Like this thing is, there we go. It went away. All right, that looks good. Thank you. LastPass, we don't need you. Okay, we should be live on YouTube. If you're in the YouTube chat, say hi. Oh, and you can see my OBS. Look at that. Move that around. Don't worry, I'm a professional. Okay, there we go. Started hearing myself in my headphones. All right. Thank you, Mr. Certainly, for helping me out. All right. Hello, everyone. I'm gonna wait just a minute or two longer before we get going. Restream. Mr. Certainly, you're so helpful. I appreciate it. Testing all my chats for me. I'll just switch back here. Mark says, I've dealt with enough professionals to know perfection is not required. Yeah, YouTube now makes you, like, they changed some settings so we can't just use Restream to update the titles. So I've actually been going in and, like, marking it as a scheduled stream, which I think actually is kind of nice. I think that works out. Hi, D Flowers. Hi, Mark Olson. Hi, Jack Gordon. D Flowers says, received my ESP32S2 1R yesterday and a TT41. That sounds like a lot of fun. Two awesome things. I have both of, well, yeah, I have both of those things on my desk. Sion asks privately whether the boards from him have arrived, and they have not. When I looked at the link you sent me, Sion, I don't know if he... I don't know if he can hear me. All right, it's been 3 minutes. Let's do some housekeeping. Let me pretend to be professional here and do my splash screen. All right, hello everyone. I'm Scott and I work for Adafruit on Circuit Python. Welcome to my deep dive. I normally do these on Fridays at 2 p.m., but Friday I'm taking off to extend my holiday weekend here in the US. So today we're doing it at 3 p.m. This is, yep, Unexpected Maker asks, why are we streaming a day early? And the answer is I'm taking tomorrow off because we have Monday. Monday is a holiday for us, so I'm taking Friday off as well because I have a general policy. I work for Adafruit. I'm a contractor. They have days that we get off for Adafruit, but I generally, as a contractor, you get flexibility on when you actually work. And my wife gets tomorrow off from her work. And so my policy generally is to take the days off she gets off, which makes sense if we're going out of town or anything. So she's taking tomorrow off, so I'm going to take tomorrow off too. So we're doing it on Thursday. An Unexpected Maker, I haven't gotten your Feather S2 boards, and I don't believe, I looked at the link you sent for tracking. I don't believe they've left Australia yet, unfortunately, which is why I was asking you for your pinout so I could mimic it with breakout PCB. Okay, it took me like 20 minutes to do housekeeping last time, so I'm going to try to do it quicker. I am paid by Adafruit. They're based in New York. They are starting to ship stuff, so if you go to Adafruit, You can check out what's available there and order it. Just have patience in terms of shipping, because they're shipping COVID related stuff first, and then they'll get to your stuff. And USPS and all of the shippers are kind of all wonky due to the pandemic as well. So just please order from Adafruit. If they don't have something in stock, make sure and check DigiKey. They might have it in stock. They're both great companies to support, so check that stuff out. That's mostly what it is. I do have 3 chats over here on the left, which is the wrong way, this way. The top one is YouTube. The middle one is Restream, which is merging Twitch, Periscope, which is Twitter, and the last one is LinkedIn, I think. We're broadcasting out to all of those. And then the bottom one is Discord. I'd totally make it bigger if I could, but the Discord overlay doesn't let that happen for some reason. So I recommend joining our Discord because our Discord lasts all week long. You can join the Discord by going to either the link. It's like not a mirror. This link here, discord.gg/Adafruit will get you there, or we have our own short link, which is adafru.it/Discord. So yeah, that's the best place to go because that lasts all week. And there's a CircuitPython channel. I'm Tannewt on there. You can find me there. I think that's about it. So the general structure of these streams is like tracking how CircuitPython on the ESP32S2 is progressing. And I start with housekeeping. I do a recap of kind of what I accomplished over the last week in terms of ESP32S2 on CircuitPython, and then I go into information on or like working on the thing that I'm like in the middle of. Tends to be about 2 hours. That should be okay. We'll see. And then the last housekeeping that I don't have on my housekeeping list that I just remembered is just a heads up. As most of you who've watched me before know, I do have a cat that loves to sleep in here with me, and he is epileptic, so occasionally he has seizures. So if you hear some cat hissing, I'll probably just mute my mic and we'll hang out for about 5 minutes and then resume the stream once he's done. I just want to keep an eye on him as he does that. That's the cat heads up. He's currently down here, so I'll be able to take a look at him a bit better. He's sound asleep, so don't feel bad for him. Okay, so let's recap. That's not recap. Actually, no. I was going to answer D Flowers' statement/question. D Flowers said, hope you're able to get Python working on the Teensy, especially since Teensy 4.1 supports USB host. CircuitPython is currently running on the Teensy 4.1. It didn't take too much effort for us to port the work we had done for Teensy 4 to Teensy 4.1. So if you go to circuitpython.org/downloads, you can download it for Teensy 4.1 right now. I have like 2 on my desk right here. Paul sent me this, which is cool, which is a breakout that he made from the Teensy 4.1 up to the same layout that has LEDs and resistor, like LEDs for every pin, so you can check the output. So that was super, super nice of him. So yeah, try it out. It definitely doesn't have USB host. We don't have USB host support for anything in CircuitPython right now. But because most of our ports use TinyUSB, once TinyUSB gains host support, it shouldn't be too much effort to support it on the platforms that support USB host through TinyUSB. Okay, so let's check out what happened in CircuitPython ESP land. So first and foremost, last week I cleaned up the changes and made a pull request, and that pull request is now merged, which is super exciting. And you can't see my screen. Let me change. Now you can see my screen. I've got GitHub up here. And I just did a different search. I'm searching for a PR by me, and I'm okay if it's closed. So here you can see the addition of the Teensy 4.1 board definition I did 10 days ago, and then the initial ESP32S2 work, which is what we finished up last time, which means that now if you want to download a bin, you can go to this Amazon. Actually, that's a bad way to show it. It's kind of a bad way. So if you go to circuitpython.org/downloads and click a board, you'll notice that there's this absolute newest box. And this is literally the latest commit to CircuitPython master. So if you click that, you get dumped into this directory, which has all the old release builds along with per language directories. And then within there, it's literally one file per commit. And then you can see it also does include the builds for the actual releases as well. So that's a great way to do testing. Now, I don't think we've actually added the ESP salas. Yeah, we haven't added the salas to the downloads page yet because we only really add them when we do a release, and we haven't actually released the stuff yet. So what you could do is you could go just to some random board. Back button doesn't work. So you could click a random board and then browse. And then when you browse, hit this bin directory, and that will take you to all the boards. And now you should be able to find the Espressif Sala one with the room module and one with the rover module. So if you have a room one and then you select your language, and now you can see like these are the 7 builds that have happened since that got merged. So that's a cool way to test if you want to be on the like very newest version of CircuitPython. Otherwise, the circuitpython.org/downloads page is the way to go. Okay, so that's a consequence of it being merged in. And that was great. Thanks for folks who chimed in. And then I quickly followed up. Like I had done, when we did the digitalio stuff, we just did the very basics of output. And so I've got this new PR out that does, let's take a look at it because I want to cover it. It's kind of tricky. It's trickier than one might imagine, and I didn't fully appreciate it until I went back and did it. So what we try to do in CircuitPython is we try to warn you, or we prevent you from using a pin, as in pin that outputs on a particular wire more than once at the same time. We don't want you to accidentally like create a digital in out and then try to use it for I2C and like have that appear to work but not actually work like you expect. So we have this tracking that happens under the hood for when a pin is already in use. And so that was one of the things. So let's just go over this PR. This merge translate is just something for us to make it easier to merge locale information. Thank you to Johnny in particular, who's been doing a lot of the Swedish translation. For those of you who don't know, we do have, I wonder if we link it from our circuitpython.org site. I think they added it to contributing. Oh, I don't think it's been merged yet. But we have this, there's this project, open source project that makes money by hosting. And so we're paying for Weblate to host the CircuitPython strings. So it's hooked up into our GitHub. So if you want to, one of the ways you can contribute to CircuitPython is translating all the error messages primarily into different languages. And this is a great way to contribute to that and manage it. And you can see here that Johnny, I think, on his own did this Swedish translation, and you can see there's just a check mark, which is awesome. So cheers to Johnny for helping with that. And if you don't see your language here or a language you speak here, there is a way to request it as well. And we're happy to add more languages. Oh yeah. the start the new translation button. Because we're seeing more translations coming in, I decided to add this like easier way from the command line to do a merge. So basically you do git merge, and then if it complains about the locale directory, you can run make merge translate, and it will fix it for you. So that's part of it. And then we go here, we can see that I added one. Johnny's a legend. Yes, indeed. We've been watching The Great, which is on Hulu, which is a kind of a dramedy about Catherine the Great, and everyone in there always says indeed. So every time I find myself saying indeed, I just think of that show. So indeed. So I'll just skip these. These are all the same thing. We make sure that the all of the new strings that get added to every language so that they're present there to make it easier for translators to just edit this bit. This is before we had WebLate, so WebLate's smarter, but yeah. And Unexpected Maker is suggesting somebody please translate to Klingon. That's totally cool. We're game for that. We actually have Pirate English as a way to practice and test translations as well. Okay, this is just a simple thing. One of the tricks or the caveats with the ESP32S2 is there's one pin GPIO 46, that is input only. And this is the first time actually that I think we've dealt with something that had an input only pin. So what I had to add is the ability to return a failure basically from switch to output and set drive mode. Because switch to output's using set drive mode internally in some cases. And so that's the Atmo one. This is the Presence one. Let me talk about that a little bit later. Later. Switch to input. Yeah, so this is the ESP's implementation. And I basically am doing this. Oh, that's get direction. So the ESP IDF, so this is in set drive mode. And if the two drive modes that we support, this is used for output only, is either open drain or regular push-pull output. And basically the IDF will return us an error if it's the pin that is input only. So in that case, now we can return digital in-out result input only, and then that gets propagated up to the switch to output as well. And yeah, let me talk about this stuff a little bit later. Let me just connect that. So that was in Common Hal. And can I make this any bigger? Can y'all read that? Or at least are you okay listening to me talk it over? So let's scroll to let's start from the bottom and work our way up. So this is shared bindings. So this is the common code that's between Python and C. And so in that code, I now have to handle the new result that it's input only. And this is where you can see that I'm saying if the result is that it's input only, we raise a not implemented error. That's subject to change because this is still being reviewed. It's not merged, but I think that's the right Python error to throw. Right. IO46 is also a strapping pin, which in my understanding is that means that the strapping pins are read at startup and stored in a separate register. But after that, it doesn't matter, from what I can tell. Like you can use it as a regular input after that. Sorry, I got a message. Okay, so that looks good. And then all I had to do here is I added the new result. And the reason that we have this enum result that we're returning is that we actually do call this API from not Python. And so we want to make sure and not raise an exception, because if we raise an exception, we could cause, we don't want to raise an exception for common HAL, because that will cause bad things to happen if the VM is not actually running. So this is just me changing like the common HAL API. Yes. Sion confirms that my understanding is correct, which is awesome. So this is me just like changing the structure and the return values for STM, because it doesn't have to deal with that. And same thing for NRF. It's amazing we're like getting all of these different ports. So this is the IMX RT1010 or 10X and LightX, which is RISC-V on FPGAs. Okay, so that is all about how I handled the input pin. Let's switch to the other side of the file. And this is one thing I did. So I actually, in this PR, I also introduced the idea of like a module. It's very, very common for ESP boards to use like the room or rover modules from Espressif. So I wanted to be able to factor common stuff out for modules, so that per board, that stuff that needs to be done for the module doesn't need to be done for the board explicitly every time. Where should I start when talking about this? I guess let's go through this file, which is the common HAL digitalio, digital in-out file. So this is what we were working on last time. You can see I deleted the logging because I don't think we need it anymore. And I basically went through this file and actually implemented everything that was in it. And we have this concept of never reset, which means usually what we do is when a VM ends, we reset all the pins so that if you have like PWM out happening, it'll be turned off. And it also means that if a VM starts up next time, it's starting from kind of a known state where there's very little state that persists across VM runs. Yeah, Bruce says he's in Canada and the long weekend was last weekend. Yep. Yeah, I heard that. Katney's in Canada said that was as well. So never reset is a way to say when you do that reset after the VM's done or before you run a VM, don't actually reset the pin, which you need for things that are like kind of not in their default input state when things are reset. And this is particularly useful in the module sense for like all the pins that connect to the like SPI RAM, SPI flash. So getting this right is important because you'll lose like connectivity that you need otherwise. So I added support for that. And then also, as I said, we also try not to, no worries, Bruce. We also try to prevent the user from using the same pin twice. So like you don't want to have two Python objects using the same pin. Because that like, I think if I remember right in MicroPython, it's the last one wins. So you could like potentially do that. Mark says I'm in pirate mode. You said R, not R. Yeah, perhaps. It's kind of my Friday since I'm taking tomorrow off. And I just had an idea for what I want to work on over the weekend. So that's try not to let it distract me. Okay, so claim pin is like within this VM session until I release the pin, like nothing else can use it. And then this reset pin number is the reverse of claiming. It's releasing a pin. And it's interesting that one's claim pin, one's pin number. We sometimes store on the SAMD, we would switch to storing pin numbers rather than pointers because pointers are 4 bytes and numbers can be 1 byte. But in this case, I don't care. We've got plenty of RAM on the ESP32S2 and we don't have to get that detailed. Um, on the left here, I actually redid the GPIO config stuff that we did last time, because I discovered that we could just call GPIO set direction, and I implemented set pull, which kind of does most of this logic already. So I just called that instead. Switch output had a similar thing where we set the level and then we just set the drive mode, which will set it to an output. And to get the direction, I had to do some fancy things, because the ESP IDF doesn't actually like have ways of reading. Like it doesn't have a get direction as far as I could tell. So I actually have to like basically look at how it's implemented and do it myself in the reverse. So I did that, and get value was easy because they had a get level. And setting the drive mode is like the same code that we had before. So yeah, there's that. And then this is another trick. This is getting the drive mode again. Like they have a way to set it, but they don't have a way to get it. So I had to do some like look at the actual registers. But I was pretty impressed. They have like structs and stuff for the registers, which is pretty nice. And then for setting the pull, the ESP IDF does the pull up and pull down independently. We don't support that in CircuitPython, so that's why it's structured this way. And then get pull, again, I had to look into the registers to see the current state. But that's it for that core. Let's just mark that as viewed. So for never reset, yeah, let's keep rolling. So this is in microcontroller.pin.c. We now have two word arrays. They're bit maps or bit masks for which pins are never reset and which pins are in use. And we have this never reset pin number, and reset pin. So reset pin number will do both never reset and in use. It will clear them both. Reset all pins will set everything to disabling the pull-ups or disabling the pulls and setting the direction to input as our default state. And it will only do that if there's a few pins in between like 23 through 25 that aren't broken out. And so this table here has zeros for it. So we just say like, oh, if the IOMUX address is 0, like that pin doesn't exist. Or if we're not supposed to reset it, like it's never reset, then we skip it as well. So this reset all pins gets called from resetting the port, which means that you start from kind of a standard place in your Python code. Claim pin just sets the bit mask in use. Pin number is free, checks both never reset and in use to make sure that they're both 0. And this common HAL MCU pin is free is really commonly used in shared bindings to like centralize all of that, the error checking for when a pin is already in use. Blah, blah, blah. I did start to add like critical section support. Like CircuitPython uses this disable interrupts, and I tried to just use a mutex. I don't think that may not be right. We might have to fix that, but for now it's fine. And then I added this concept of modules because there's common pins for modules, the SPI flash in particular, that we don't want to reset ever. And so I just added this never reset module internal pins. And there's now a modules directory with the name of the module that gets swapped out in the build stuff. It's 6 pins for the room and 7 pins for the rover, because the rover's got another CS pin for RAM. One thing I was thinking would be interesting for an ESP32S2 board would to actually put the flash and RAM on separate SPI buses. I think would be cool, because otherwise they're a shared resource and you can't access them both concurrently. So this is the default setting, is that you're not using a module. And this is the other. There's our none version, just doesn't reset anything. And then our header for it. And then in our boards directory, now we're setting what module it's using here and here. And we're also never resetting both the USB and the debug UARTs, which are kind of like a board specific thing because the board defines how they're hooked up. Like the fact that it has USB is up to the board. And this is how we do it in the make file, is we use this substitution to include the .c. So we end up only with one copy of the same function. This stuff is pretty similar. And then just in port.c, this is where we're tied into never resetting the internal pins and where we also reset all pins. Okay. Any questions? That was an early deep dive. Let's take a breather. This is out for review. If you want to review it, that'd be awesome. Dan's mostly done the review. Yeah. If somebody can think of a better name, let me know. Okay, let's move on. So, really, no questions. I had to point it out last time, right? That we didn't have that many questions coming in. I really don't like that. I have to see the live chat in the YouTube thing. It says there's 13 viewers, but the web page says 28 watching now. Who knows which one's right? Whatever. Okay. So digitalio is basically done once this PR is merged in. The next thing to work on is BusIO. Mark's routing the last two traces on the board, making a breakout for the Sala. And I asked Sion for his pinout for his feathers so that I could make a equivalent like board that goes on the bottom of a Sala with the same pinout as his feathers and a USB connector. P-Boy said, then last week was an episode of biography. I don't know what that means. You could explain it. Okay, so the next thing to do after digitalio is BusIO. And BusIO is probably one of the most powerful modules in CircuitPython. And so let's pull it up and let's talk. I want to talk about BusIO and the buses it supports. 3 of the 4. So we can do core modules, and I'm actually going to make this latest. And it might break then. Nope, that worked. So if you notice, this changed because we switched to stubs, so the layout's different. But I want BusIO. So these are all serial buses. Oh yeah, lots of questions about me. Yes, that's true. We don't need personal questions like last time. I want questions about electronics. So I2C, let's see. I should put a table of contents at the top. So what we have here is, and we can see it on the left-hand side, is we have, within BusIO, we have I2C, we have one wire, which is not natively or hardware supported. It's just, we usually bit bang it. We have SPI, we have UART, and this parity thing is like an enum style class used by UART. So it's not actually a different type of bus. And I wanted to take some time to just talk through the differences and why you would use one versus the other for I2C, SPI, and UART. Hopefully that's interesting. Raise your hand if that's interesting. Um, but it's something that I've thought a lot about, and I think that some folks getting into electronics don't really understand the trade-offs. So first and foremost, let's talk I squared C. In terms of Adafruit land, this is by far the most used bus. So let me step back one step and say a bus I think of as a it's not just a single wire usually. It's more than one wire. So a bus, I think that is the definition of bus. All right, we got raised hands. Awesome. So what a bus is it's a collection of wires that work together, is what I would say. And that they work together in an amorphous way when you talk about a bus. But once you talk about protocol, the protocol that the bus implements, now you're starting to add information or agreement on how all the wires in a bus are used and what for. So let's first talk about I squared C. So I2C. It takes 2 pins. It takes SCL, which is the clock pin, and SDA, which is the data pin. And a lot of buses, I was trying to think of examples of buses that don't have clocks, and we'll get to that. But a clock line is usually used as a way to convey from one end of the wire to the other when data is valid and when it can be changed, is what I would say. And please, if I'm losing some subtleties, let me know. But that usually, the way that usually works is the bus will say perhaps like data is valid specifically when it goes from low to high. That's called a rising edge. An edge is when the signal changes. So you have from low to high, you get a rising edge, and from high to low, you get a falling edge. And those are really useful concepts because the transistors on the connected to the wire work on kind of those transitions. So a clock line or a clock wire is really helpful for conveying across different chips when data is valid and when it can be changed. And the speed of that clock basically dictates how fast your data gets moved or how frequently you can change the data that goes along with that clock signal. And if you have, there's kind of these two types of buses or categories of buses. One is serial buses, where it's basically one wire that is one or two wires that are basically conveying one bit at a time, where a bit is 1 or 0. And then you could also have parallel buses where you might have one clock signal and then 8 wires that are all carrying data at the same time. And that's a parallel bus. So I hope I'm on the right track with this. I've not practiced this explanation, but I think I've learned a lot in the last 5 years. So let me keep going. So I squared C is 2 wires. It's the clock pin, as we talked about, which tells us when data can be changed and when it's valid. And then SDA is a data wire. And this data wire is, so the clock pin is only changed by the commonly the term is master and slave. That's a bad term, and we should all try to move away from it because of the connotations of those 2 words. And I'm trying to remember what some of the alternatives are, but basically the controller and the control-E, the thing being controlled. So in this case, for example, like a microcontroller like the ESP32S2 would be the controller. It's responsible for changing that clock line and dictating it always. almost always. And then we'll get that into just a sec. And then the SDA line, what makes I2C very powerful and very unique is that the SDA line can be used or controlled by both the controller and kind of the controllee, or master and slave in that terminology. That is a pretty unique property, and certainly a unique property of I2C, where kind of both ends can control both wires. And the way that I2C achieves that is that basically neither of those sides, or the things that are connected to the wires that make up the bus, no one actually makes a 1, which is kind of weird. So basically they're all sending zeros back to each other, and the way that they can read ones in is because there's actually resistors that kind of default the state of the wire to 1. So if nobody connected to the wire is connecting it to ground and setting it 0, the whole the voltage of the wire itself gets pulled up, because there's a resistor that has connected it to the high value, which is 1. So if only I had a way to draw. So we talked about edges, and on I2C, the falling edge tends to be very sharp. And that's because you can very quickly drain away the current that's on the wire, or the capacitance on the wire. Whereas the ones get actually slowly formed, or formed not quite as quickly, because it takes a little time to suck, or I guess it's not sucking, it's like pushing charge back into the wire when nothing's connected or nothing's draining it, because it's connected through the resistor or resistors. So that, when you're thinking about how fast you can clock I2C, you have to consider like the value of that resistor and how quickly it can basically give you a 1 by pulling up the wire. So that is really cool. That means that like both sides can control the wire without having to worry about the case where one sets it to 0 and one sets it to 1, which would be a short circuit. Basically because nobody connected to the wire is actually setting 1. They're just always like, oh, if we both set 0, that's fine. And if we need a 1, we just don't say anything. So this is used on the clock line in I2C, where the controllee can actually set it to 0 to say like, hey, hold on. Basically the controller needs to make sure that like it can actually clock the line, or by changing the line. And then it's kind of up to agreement on the data that's being sent when the controller is setting zeros, or when the controllee is sending zeros on the data line. Simple topic, deep dive still. The last thing to talk about is, because it has this nice property where like nobody's ever setting a 1, everybody's only setting a 0. It also means that you can actually have multiple devices connected at the same time. So you can have like one controller and 2 controllees in this terminology that I'm making up. But I have, let me show. Actually, maybe I should just switch my camera. So this is how I store a lot of my breakouts. It's like one big anti-static mat. And you can see I have all these quick connectors where they have 4 wires. And these actually use I2C. Quick is the SparkFun name, and there's a compatible version or thing from Adafruit called Stemma. Stemma QT is the small plug. This is not the small plug. This is the large plug. This wire is not going to be very useful. But it's interesting because captain and conscripts, principal and subordinates. Yeah, a lot of people still use master and slave. But yeah. DCD says very cool way to organize boards. Yeah, I've got enough boards. I got to figure out how not to use packaging. I'm still working on that. It's just I just continually get more boards in, and I don't have a ton of space. So you'll notice that this is actually 4 wires, and it's I2C, so that has clock and data, but it also has ground, which basically you'll always find as a wire as well, because in order for the voltages to make sense, you have to have a reference, because voltage is really the difference between like 2 spots, and also power. So like high voltages on here as well. Dennis says primary and secondary are also an alternative names. Yeah, those are better too. There's still like, I forget who it was like came up with. There's another set of alternatives that I'm not remembering. Power is useful, not from like a I2C perspective, but it's useful from a like, I want to power the thing. Like I want the sensor to be powered. Bruce says, I never realized that the alternative naming was a thing. Now I'm actively Googling it. Yeah, I looked for it at once, and I'll have to look again. I'm not going to look on the stream because I want to talk more buses, but yeah, there is something, and it would be cool that we minion is a good idea. I like that. So on I2C, you can have multiple minions. And so the question becomes, if there's multiple minions on the I2C bus, how do they know which one you're talking to? So if you've ever used I2C, you'll notice that host and device, Ryan says, that's a good idea too. Yeah, that's good. Oh, lots of good alternatives. So with multiple devices on the I2C bus, you have to worry about how do the devices know which the host is talking to. And the way that I2C does that is that it includes 1 bit. It always starts with one. I think it might be 8th, but it starts with 1 bit to say whether you're reading or writing, like the type of the transaction that's starting. And then there's 7 bits of address. So each device on the I2C bus knows its address and can then tell whether the host is talking to it or not. And you'll see sometimes that devices have the ability to change their address, and that's really useful if you have multiple copies of the same like IC on the same bus. Timon says, currently going through the German translation of CircuitPython. Seems it's mostly complete, but somebody made a ton of suggestions only. Interesting. Thanks, Timon. So that has a downside, and this is why I wanted to talk about it. The downside of I2C is that it's slow. And it's slow for two reasons primarily. One, you can only clock it so fast because as we talked about, it has a pull-up that takes some time depending on the value of the resistor. And then it also is slow because every time you do a transaction, you have to spend 7 bits worth of time or 7 bits worth of time saying who you're talking to. And that can take some time as well. And then, of course, you only have 1 pin for data. So I2C is typically clocked at 100 kilohertz, 400 kilohertz, and a megahertz is what I've seen. And that is what that frequency means is like how quickly does the clock go up and then back down and then up again. So like 1 cycle of the clock. So 1 megahertz is 1 microsecond. Yeah, 1 microsecond for that form to happen. So that's I2C, and it's super useful, and we use it a lot because you can daisy chain. You only need those 2 pins everywhere, but it's slow. Any other questions about I2C? Lots of good ideas on alternatives for master and slave. I'm not going to talk about one wire because I don't actually know it very well. And it's only really used in like temperature sensors. Bruce says, I think they have a 5 megahertz crazy fast mode they use for some differing protocols for I2C, I assume. But you have to really like have a lot of control over what's connected to it to make sure that you can actually pull up that quickly. Host and client agent, Smith says. Controller and peripheral. I feel like it'll ring a bell, the one that I've heard before. It was like, I saw it on some project in GitHub where they like actually changed the docs for it, but I don't remember what it was. These are all better options than master and slave, so keep them up. Okay, so let's move on from I2C. We talked about it. We're almost an hour in, and I should see if I couldn't get I2C going at the end. But I want to talk about SPI and I want to talk about UART before I do that. So SPI is, it has a clock, leader and follower, Dennis suggests as well. So one of the lines on SPI is clock. And I tried to standardize in CircuitPython that the clock pin, because you almost always have it, is the first option always. If we have a clock pin, it's the first option. And then there's the MOSI pin, which is making it. Actually, here we go. So Abominable has a question. If there are only a few address pins on a board are exposed, I think the Adafruit server bonnet only has 5. Is there a standard for setting the rest, like a safe assumption if you're using the raw protocol? So remember that with address pins, you get 2 to the number of address pins in terms of options. So if there's 5, that's actually a lot of options. So you could have 32. 2 times 2 is 4, 8, 16, 32 options. So you could have 32 of those things on the same bus. And then, we can keep talking I2C. If you all have questions about I2C, good. And then, actually, we can talk about the CircuitPython API is what Simon was wanting to talk about. The rest of the pins are usually defined by the IC. So look on the datasheet of the IC for what the other pins are talking about. No, Simon, I don't think we did. So hopefully, Abominable, that answers your question. Follow up in the Discord chat if you have more questions of follow up. So I'll ask. So Simon asks on YouTube. I wanted to ask about how to assign addresses in I2C for CircuitPython. It says I'll save it for later, but we'll talk about it now. So this is an interesting question. So in CircuitPython, we've chosen to separate the idea of a bus and a device on a bus. And we actually make that distinction. The buses are implemented in C, but the bus devices, we have a library called bus device. That is meant to embody a device that's on a bus. There's probably a better way for me to say it. We can hit the docs. I don't know if most people know this, but if you go to the GitHub for a particular library, there's a docs passing, ideally. It might say failing, but ideally it's passing. Spam. You can click docs passing, and that will take you to the docs for that particular library. So here you can see that we have both I2C bus device and SPI bus device. So if we just say I2C device, this is what takes the I2C. This is the bus, and then device address. We'll talk about SPI in just a little bit. But so this is the short answer to how to say what the device's address is in CircuitPython is you should really use an I2C device to do it, and give it the bus that it uses. One thing that bus device does for you is it does this try lock and unlock, which we have for both I2C and BusIO or SPI, because a bus can have multiple devices on it, and you need to be able to make sure that like two pieces of code aren't trying to write to the bus at the same time. And you say, oh, but you don't support concurrency in CircuitPython. And that's true, except for the fact that sometimes you're sharing a bus with internals, CircuitPython internals. For example, you could have like the SPI flash that CircuitPython is using is on a SPI bus that is also the SPI bus that's broken out by the board, and you want to be able to use those two at the same time. So locking is really helpful. And so take a look at bus device because it handles the locking for you. Honest Pangolin 685 says, on WebLate, some artificial translations got entered as suggestions from Anonymous. Sometimes they seem okay, sometimes they're wrong. And it changes the %Ds into percent space D every time, which is not good. Yeah, I hope they're all suggestions and then people can mark them as good. That would be good. WebLate's super new, so if you have feedback for us, let me know. Okay, so to continue on Simon's question, in the SPI bus itself, in CircuitPython, which we implement in C, we just always take in the 7-bit address. In this read from into, does a read from that address and writes it into a buffer, and then write to does the opposite, it goes the other direction. And then write to, then read from allows you to write a bit of information and then read, which is really common in, if you want to say like, I want to operate, I want to read this particular register. So read to this device, this register address, and then write. What did I say? Yeah, it's helpful for reading a register. And the other thing I should point out is this scan. So this allows you to find all of the devices on the bus. And the way that it does is it literally just loops through all the things and just tries to like see. There's I2C has this notion of acknowledgements that I'm not going to get into because I don't remember. But you can tell whether something's responding on a particular address or not. And that's really useful. I think we have probe as well. Maybe not. But when you're writing a device driver, it's really useful for you to say, and I think bus device does this automatically. But if you say like, I have a device at this address, like you should check as soon as you can that there's something at that address so that you can raise an exception to the user saying like, you said this address exists and I can't find it, is really useful. So scanning and probing is really handy for that. All right. Last check for I2C. I mean, you can ask me later. It's fine. I can go back to I2C. I2C is very, very, very useful. It's just kind of slow. Simon says, scanning is super useful. I always run it before doing anything I2C. Yeah, very helpful. It's a great way to know you connected it right. Maybe I should have had the Salier up and we could actually look at these, but maybe we'll get there. We got an hour more, and I have 2 more things to talk about before I start coding a little bit on I2C. Okay, let's talk SPI. So what are ways that you can go faster? And this is what SPI is good at. SPI is good because it has a clock, and that clock must be set or is always provided by the host. I'll use host device for this. And if you're reading docs in C master and slave, and we're going to hit that in just a second, just know that I'm trying to get away from that terminology. So clock is always provided by the master, the host. And then there's 2 data pins traditionally in SPI. There's master out, slave in, which is what MOSI stands for. So that is the host is responsible for sending bits to the device. And then to get data going the other direction, we have a separate wire that is the device setting data and the host reading it in, which is the MISO, master in, slave out wire. And frequency, again, this determines the frequency of the clock. So basically that determines how many bits you can get going through, because again, we talked about a clock is fundamentally when you can change change your data and when it's valid. SPI can be confusing because it allows you to configure that notion of when the data is valid. So this is actually bad. We have configure baud rate and then frequency, and those mean the same thing. Zach suggests initiator and responder. Also good. Everybody has so many great ideas. I don't know why we're still using master and slave. It's good to standardize, but I don't know. Okay, so this is a bad API design, so you can blame me for this. That configure takes baud rate, but we actually call it frequency if we read it, which is silly. Yeah, Agent Smith says clock is like a heartbeat, and each pulse needs to be in sync. Ooh, that leads to a good topic. Let's circle back to, maybe we should talk about that. We're doing a deep dive. We can talk about being in sync. Yeah, I know. Bruce says, unfortunately, using the acronyms for MISO and MOSI mean you have to continually translate in your head to whatever is currently used. Yeah, it's unfortunate. Which is why, here's the challenge. Y'all have come up with great alternative terms. The question is, can you do it where M and S are the starting letters still? Okay, so the other thing that I talked about is not NSYNC, not the band. Come on, Mark. So SPI is interesting because it allows you to define what portion of the clock signal the data is valid on. So that is dictated by polarity and phase. And you can see here that phase is defined as the edge of the clock that data is captured. So that tells you which edge is considered valid. Again, we have locking. Again, we have write, read into. So this write and read into are actually... Mark suggests mark in, Scott out. What if you have multiple Scots on your bus? That's a funny one. Okay. So with SPI, if you have both MOSI and MISO, you are like, there's always data going both directions. P-Boy says we have a winner for Mark in, Scott out. And Bruce says, I am on it. M is Maleficent and S is Sleeping Beauties. All right. Nice. Yeah, so SPI, if you hook up both wires, the data is always going both directions because those wires are exclusive in each direction. So when you write and when you read, you are actually still going, like data is still all going the same way still. Mr. certainly suggests Mufasa and Scar. I think we're on a Disney kick here. One interesting thing is if you're reading for SPI, you can, some things care about what value you're giving the other direction. So we have the ability to set that here. And I'm forgetting that SPI is actually 4 wires because I haven't talked about that yet. So SPI itself, as the bus itself, is 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 3 wires, as we've talked about. But, manager subordinate. That's a good one. Bruce says we have no work ethic here, or squirrel, I assume. So we didn't talk about SPI buses or SPI devices at all. Ryan says, I never understood why the SPI peripheral interface didn't call devices peripherals. Yeah, serial peripheral interface didn't call devices peripherals. That's a really, that doesn't make any sense. It should be peripheral. All right, we're on to something here, folks. Okay. I'm getting my chapstick out. So while I said that an advantage of I2C is that you can connect multiple devices or peripherals to the bus, you can do that for SPI as well. What we're not seeing here is that the way that happens is you have a fourth wire that is characterizing or encoding to the device whether it should be paying attention to the bus or not. And that's called chip select. So if we look at, I think I have the schematic up. Yeah, let's look at a schematic here. This is the wrong one. This is the Salva schematic. But I want to look at, I mentioned this earlier actually, about, here we go. So this is the data sheet for the rover. And if you look down at the bottom, there is a schematic for what is on the module itself. So I'm going to try to make this as big as I can. I hope you can, oh, you can't see it. You're not looking at my screen. Now you can see my screen. I'm glad I saw that before I spent like 5 minutes talking about this. So the thing with SPI is that you have to have one wire for chip select per device that's on it. And it still means that the other 3 wires are shared, meaning you can't talk to both devices concurrently. You have to be only talking to one at a time. And that's kind of unfortunate. And I'm not sharing the doc. You don't see a schematic? It might be a little small. I'll try to make it as big as I can. ST calls the pins SDI and SDO. Device in and device out. So this is the actual ESP chip, and then they just like name all the pins. But at the bottom here, and I'll try to make this even bigger, they have 2 chips that are connected over. Okay. All right. Abominable says it's just chat latency. You are. Okay, I see what people are saying. I wasn't showing the doc, and then I realized I wasn't showing it, and then yeah. Perfect. Yeah, sorry about that. I think the YouTube stream is actually a little bit further behind than like Twitch. I could change the setting, but I don't know. Not my forte. So here's an example of a device that's connected to a SPI bus. And so these are the blocks. They look identical or nearly identical. The left one is flash and the right one is the RAM. And these red labels are the name of the wire that they're connected to. So physically, if the label is the same, the wire is the same. So DI, device in, would be SPI D. Sorry. And then we can see here on the PS RAM, it's also the same chip. So these 2 chips are on the same SPI bus. The only thing that's different is the SPI CS0 and SPI CS1, which CS means chip select. So it decides which of these two chips the host or the manager is, I'm just picking terms, is talking to. So this is not great in terms of competing with I2C in terms of number of devices, because every time you add a new device, you have to add a new wire, right? Whereas I2C is always just the same number of wires that just are daisy chained. And there is that still exclusivity that has to happen between the two devices, which is why I think it would be interesting if the module didn't do this, that the module actually put the RAM and the flash on completely separate SPI buses. So I think we're about done with SPI. If you have questions about SPI, please ask them now, because there is this chat latency. The last thing I want to talk about is the fact that there are kind of faster versions, more parallel versions of SPI, which is really interesting. So we talked about SPI being a clock and two lines, one going each way. But there are modes that actually do more like simultaneous data out or parallel data out. The one that we've seen most common is main and secondary. We've had primary and secondary, but not main and secondary. So there's a version of SPI called QSPI, and that is quad SPI, meaning that when data is being read, which is the most common thing, I think, typically, especially when you're like reading from flash or reading from RAM, you can basically transmit the data over 4 wires instead of just the one. And that means that given the same clock speed, you can get 4 times the data going over it. So that's, I think there's this kind of trend in computing where you computers get faster, are able to handle faster signals, and that leads to this desire to be very serial oriented, so very few wires, but changing signals really fast to transfer data. But then like you hit this limit of like how fast you can go, but you still want more data, so you add more wires, you get more parallel, and then like maybe there's another technology that happens means that you can go faster again, so you like limit the number of wires again. And like I think that's kind of a trend that I've seen, which is really interesting. I can't quite think of an example, but I think in terms of where we are at with CircuitPython and the speeds that we're seeing, we're definitely in that phase of like we're switching to like for low cost PCBs where you don't have to worry about like really high frequency signals. Like it's better to go parallel because you don't have to go faster to do more data. You just do more wires. So that's QSPI is a little tricky because you can actually end up doing like a little bit of like regular SPI and then you do quad SPI, and like you have to negotiate that and you have to set modes and stuff. So when this is hooked up, even though it's hooked up like a regular SPI, it's actually you can do dual SPI and you can do quad SPI, and there are actually some chips that can do octo SPI as well. That might be called Hyper Flash. Hyper RAM can do octo. But that's pretty interesting. And that can mean that SPI can be really quick because SPI can be clocked up to so Agent Smith points out that the transition from IDE to SATA in terms of hard drives was one of those switches between, a big ribbon cable that's very parallel to like a few wires that are much faster. And then the other thing, what was I going to say? I think I'm losing it. QSPI. I lost it. OctoSPI. I was going to say that SPI can also be faster because it's not relying on the pull-up, which means you can find these flash chips that you can clock SPI up to like 133 megahertz, which is a lot faster than what we talked about with I2C. Although you do have to be aware of that you have to be aware of the fact that the SPI or the flash itself can only go so fast. So sometimes what you'll find is that you can either do very parallel at a quarter speed, or you can do very serial at 4 times the speed, because the flashes can only be managed so fast. Timon points out that DDR RAM does both. It's many super fast wires. Yeah. Yeah, and D Flowers also pointed out that the same IDE to SATA, except called it SCSI. Yep. Awesome. So I'm on to something. And then Abominable also says, just something to mention, I2C and other bidirectional protocols are notoriously harder to level shift than alternatives. So if you're using a 3.3 volt sensor with a 5 volt microcontroller, you may encounter trouble. So just a heads up for that. I did answer somebody on the Adafruit support forums about like TTL logic level stuff. So basically the way that you decide whether you have a 1 or 0 is there's like a range of voltages that get counted. I should probably not get into these weeds too. I don't know them as well. Basically, like how low does a voltage need to be to count as a 0, and how high does it have to be to count as a 1? And then that changes depending on how you create like the process that you constructed your transistors. I'm not going to get in there. Timon also points out there's a very easy level translator setup with just 2 MOSFETs for I2C though, per line. Yeah, so I think that's one thing that's one of the differences, going back to I2C, between Quick and Stemma QT, is that I believe like the Stemma QT supported stuff is can work on 3 volts or 5 volts. So like all of these Stemma QT boards have regulators that go, if they're natively 3.3, they go down, and they also do the logic level shifting, I think, which is why it's called something different. You can just see technical specs. Adafruit product code 757. Yeah, here's the schematic for it. Yep. Yeah, so if you're doing I2C, this is how you can do a logic level shifter. And we talked about this idea. You can see that it has 4 resistors, 1, 2, 3, 4, 1 for each wire on each side. And this is basically producing the ones, and the ones are different, right? Because you're going from 5 volt to 3 volt or vice versa. And then these other, the transistors are actually just controlling the direction of your zeros, or like being able to transfer zeros across, which is weird. But yeah, it's clever. And there's, yeah, Adafruit product 757 is that just on that. Okay, let's do UART. Maybe we can cover it a little bit quicker. Yeah, Tabone says it's a pretty nifty idea, and I think it's originally from an old NXP app. I think you're right. All right, let's talk about the fourth. So I would say that I2C and SPI are by far the most common things we see. UART is a different beast, and it's not that common in the stuff that you'll see Adafruit support, but it is very common in GPSs in particular, and actually like higher level control schemes. So if we look at in CircuitPython, we have a TX pin and we have an RX pin. Now note, we don't have a clock pin. So this is why I was like, Oh wait, not all buses have clocks. And the reason that is because when you set up a UART, you tell it how fast the bits are coming. And then there's logic in the thing that implements UART to actually figure out like how things line up. And then bits tells you how many bits you expect to see at a time. Parity tells you whether there's actually like an extra bit added to make sure that you receive the data right. And then also receive buffer size. So like in the first two cases, as the host, you dictate the clock. So you always know when you're going to get data back in. But in UART, it's different because the other thing is can just send it to you whenever. And so in CircuitPython, because we don't have interrupts, we do the things that happen as you're doing stuff under the hood for you. And in the UART case, we have just this, we maintain a buffer for you of bytes that are coming in. And that's like, you'll notice this is kind of a very different API. So like we can tell you how many bytes we've already gotten. Timeout is used for like, if you're trying to read a certain number of bytes, how long should we wait until we say like, we don't have those. And I don't know of any way to actually share a UART. So like you're only ever going to be talking to one other thing. And it could only be in one direction or the other as well. So TX and RX are not both required. And Agent Smith points out that it's called the Universal Asynchronous Receive and Transmit, is what UART stands for. Thank you. Okay, so this is, how would I say why it's useful? Yeah, we're doing the basic buses. Timon points out, I also recently learned about Manchester encoding, which encodes clock into the data signal and can run over a single line. Often used on differential buses like DisplayPort. Aux. I think that's it. And David points out that there are multi-drop UART streams too, which I didn't know about. I've not seen them in use. Mark points out in YouTube that RS48485 is the shared UART as well. Yeah, that's all fancy stuff I don't do much. CAN is another common bus that we still don't support and people would love to. Hey, Johnny's in the chat. Thanks for watching. And thank you again for all the translations. We talked about that earlier. Yeah, so that's UART. It's very common in for GPSs. So typically what you'll see is you'll basically get ASCII characters back. So it'll be kind of like human readable when you're looking at the UART stuff. Whereas like I2C and SPI tend to be like binary encoded and not necessarily human readable. But like for a GPS, it'll actually spit out a line that's like comma separated, like ASCII encoded values. So that's pretty common with UART. And it's actually also commonly used for like doing something like a REPL, where you're like sending characters and receiving characters. For the previous ESP chips, the way that the reason you had like a serial connection, which is I think also just another term for UART, is that the USB or the older ESP chips were paired with a thing that converted transmitted bytes to a TX line, and then the bytes received on RX line back up the serial as well. And then I also should point out that whereas with I2C and SPI, when you're connecting them up, if both things have things labeled SDA, you connect those two, and if they have an SCL, you connect those two. UART is weird in that that's not how you do it. And this gets me every time, or gets me a lot, where with UART, one pin will be labeled TX, and then you connect it to RX on the other side, and then vice versa. So it'll have a TX and you connect it to RX. So the labels don't match in the way that you connect UARTs together. Ah, Anecdata says there was a Discord question the other day about whether a TX line can be read only by multiple devices, RX, perhaps with some kind of isolation or buffering. I think you could just attach them both to the line and do it. Agent Smith also points out that UARTs are good because they can be used over long distances. Summersoft points out that the ESP port of MicroPython has dupe term, which allows you to have like 2 UARTs as the way to do the serial stuff. Oh, yes. It's depending on which end you're at. Okay, cool. I think we covered UART. And I'll cover any other UART things as they come up. But in the last half hour or so, let's just talk about how BusIO is implemented in CircuitPython. And I think the way that I'm going to do that, yeah, Mark points out that logic analyzers are basically a second transmit reader. Yep. Okay. I've done a lot of talking. My voice is starting to get tired, which is why I want to do some coding. I think I want to merge. Nice. Mark routed his breakout. Okay, I think this is going to work perfectly. So this is Sublime Merge. I haven't paid for it, which is why it says it's unregistered. I haven't found a Git program that I really like. I really like GitHub as a way to inspect things that are changing. So yeah, I wish it was. I wish it did something. I can't figure out how to do some things I'd love to be able to do. So these are the changes that I've started making yesterday. And we'll look at the untracked files as well in just a second. And maybe I want to track them because it might give me a better diff. But the first thing I did is I just made a helper to unpack the pin number out of a pin object. So I can just call reset pin. I don't have to say reset pin number. And I added to the header. And I also turned on both bitbang because bitbang only uses... Mark asks what's wrong with source tree. I tried it and it didn't stick either. One thing I like about this is that it allows you to stage certain pieces. It's really nice. Or you could discard certain pieces as well. So like if you have like a bunch of logging in certain places, you can just discard it from here, which is nice. And then the other thing I did is I copied common hal BusIO from the atmel samd directory into the ESP32S2 directory. And all I did was, you're not going to be able to see it, but I like commented out the implementation, which I'll basically delete as I re-implement it on the ESP32S2. But I had to comment it out so that I could at least get everything to build. So most of these are not that interesting, but I2C I did start. And instead of showing it here, let me show it in Sublime Text, the other Sublime program. All right, I'll take a look at source tree again. I use Sublime Text though, so that's one of the reasons I was looking at merge as well. Okay. I think I have way more stuff open here than I need. I definitely do. You can see I have the module stuff open still. So I'm just going to I want this open. Close everything else. So this is ESP32S2 common hal BusIO I2C. And as you can see, I've commented a bunch of stuff out, but I've actually started to work on it. Summersoft says, that's my favorite part of Atom's Git integration. Saves me from having to commit as often as I should. Yeah, the hunk staging stuff. Yeah. Editors like Atom and VS Code are just so slow. They try to do everything and they never do it very well for me. It bothers me. VS Code bothers me because it's constantly popping stuff up in the right-hand corner. No, I don't need it. So yeah, I'm liking Sublime generally. It does feel a bit like a regression based on what I could do on the left-hand side, but it's all right. Okay, so I don't think this will compile, but I did start looking at it. One thing I was thinking about is how to implement the lock. So as I said before, like a particular bus might be shared amongst more than one thing. And so I was planning on using, I was planning on using a static semaphore from FreeRTOS to handle that. Summersoft says, you're not wrong, haha. VS Code's info popping wears on me as well. Yeah. Yeah, we could talk about more of that, but I don't want to dog on it. So that's how we track the lock. And then I was looking at the APIs, the IDF APIs, which I will click and pull up. I was looking at SPI, but I don't think we'll get to that today. Interesting. Mark says, I agree VS Code is too slow, or so slow, but I tried to switch back to Sublime and the lack of integrated terminal was too much. Yeah, I don't use that. I don't use an integrated terminal. I'm just so slow, I just have to like click between things. I'm definitely like not a power user per se. Okay, so looking at the API reference for the ESP, one thing that's interesting and I haven't handled yet is the fact that the ESP32S2, this says regular ESP32, but the S2 is, I think is true as well, is that they have two peripherals that manage I2C. And in CircuitPython, what happens is that when you give us the pins that you want I2C to be on, we'll make it happen with a hardware peripheral if we can, and if we can't, we will throw an exception. So one thing I have to do is because the ESP32S2 is really cool and it allows us to just route to any pin, we basically just need to track whether we're using the first one and the second one. If we're using the first one, we pick the second one and we're done. If we're using both, then we raise an exception and say, hey, like we don't have any more. So that's something I could do now. And it's super useful, or it's super easy because it can map to any pin. With something like the SAMD where it doesn't have a full pin mux, it like for every pin it's connected to two circoms, and there's like all this complicated logic about like for the things connected to the pins you gave me, are they available and can I use them, and what are they? And yeah, there's a ton of logic there, which I like the API, but it's a lot of logic and it's a lot of code size, which is interesting. Simon says, why would you need two I2C controllers when you can have a lot of devices on a single controller? That is a great question. And the answer is that you can still, if you have a lot of devices on one line, only one device can talk at a time. So if you have two I2C controllers, you can actually then have them talking concurrently at the same time. Also, if you have a device that doesn't allow you to change its address, you may actually want to connect two separate I2C buses instead. Yeah, Mark says congestion. Basically the idea that like only one thing can use the bus at a time is congestion. So yeah, great question, Simon. And that's true for SPI as well. Okay. So driver usage, I love this when I see this in a data sheet. It basically tells you the order of things that you should do. So first, you should configure it. Second, you should install the driver. And then it tells you how to construct communications as a master or slave, interrupts, customizing timings and stuff, and then how to shut it all down. Blah, blah, blah. Picking the pins, saying whether you're slave or master. There is this 10-bit address mode, but I don't think we support it in CircuitPython. I guess this is in slave mode, which we do support in CircuitPython, but it's way not a priority to do. And it's not part of BusIO, so we won't do that anytime soon. Installing the driver. And then this is pretty interesting. I haven't seen this happen before, but this is talking about how to basically set up the order that things are going to happen in. So you say link create, start, write byte, write, stop, begin, wait for it, and then delete it at the end. I'm wondering how many allocations this actually does. I'm hoping none, because I'd like to not allocate anything when I do this. This is something we talked about weeks ago now, but like the idea that like Python's allocating stuff and the IDF under the hood is allocating stuff, and it has all the same memory allocation problems we have in CircuitPython, which is a topic for another day. But yeah, this will be kind of interesting. Maybe what we should do is, we got like 20-ish minutes left. I wonder if what we should do is just try to get scan working. Which would allow us to just see if it works or get something working. I definitely have to do the like track which one's in use. So let's maybe start there because that's easy. But it doesn't have the joy of like seeing a number pop up. Yeah, I like the idea of doing scan actually. Let's go through here and let's look. So, oh yeah, I have to do this as well. So one thing we have the ability to do, or we attempt to do in CircuitPython, is that we attempt to make sure that you have pull-ups on your I2C bus. I don't need to do this now. We can do this later. But basically, this is the Atmel SAMD version. And we basically try to pull the bus down. We wait a while. That basically drains all the current from it. And then we turn that off. We wait, and then we see if it's back high again. So that's one way that we can try to detect whether the like bus will be pulled up. Although this is interesting because if we pull it down, we may not be able to pull it down, which is interesting. And maybe that's why we're having problems with this, but we have the ability to turn it off. So I'm gonna ignore that today. This is setting the pin function, which is something that this param config is going to do for us. So I'm just going to delete that. And we don't have to worry about that. And mode, I need to figure out the constant that goes there. Clock rate is always 0. Baud rate is in kilohertz. I don't know what that's from. That's probably a note for this I2C or the SAMD version. And it's saying unsupported baud rate. So this I2C param config, let's take a look at see what that is. Do I remember where that is in the IDF? I think I do. I think I have it open. Maybe. This is all the low level stuff. I2, yeah, that's too low level. I think it's in driver. I like that most of this is open source. There's definitely some binary blobs, but I haven't dealt with that yet. Open source is the way to go because I like to look at how it actually works. This is interesting too because there are actually error strings. Ooh, this might have the master command defined that I need. Oh, it just says mode. Driver install. Driver delete. Param config. This is what we want. Oh, there's. Let's snag this. That sounded like thunder. We don't usually have thunder. Let me pull it up. Kind of looks like it. Oh, maybe not. I'm just getting distracted by the Doppler. Okay, this is set. Pull up enable. Let's disable that for now. What does that need to be? It's just, maybe that's a bool. For now, let's not worry about the case where we're trying to use internal pull-ups, which I don't think we allow. Oh, and there's the correct mode. Okie doke. And let's see what param config. It can return non-okay, which might do the pin setting. So in this case, we also do have to check for unsupported pins, which I have this note for myself of make sure SCL and SCR are input only, which I assume is covered by this. So let's just do a check here. If result, we'll add it later. Let's just assume that it's because I don't know if it's already checking which I2C peripherals in use or not. But for now, we'll just do that. And what's the return type? ESP32S2 result equals that. And then driver install is going to do something too. It's checking a bunch of stuff. Ooh, go-to statements. I do not like go-to statements. Wow. Look at all those things it allocates. ESP fail. All right, well, we can check that as well. We don't need, we'll just reuse that. And it cleared everything. So let's do this OS error. Just inherit it. OS errors aren't great because they don't have very good error messages. Ah, y'all went quiet again. All right, and if we get down to the bottom, we've claimed it. Hi, Dafa. I have the YouTube chat open twice. It's distracting me. It doesn't get the text message or the chat messages at the same time, which is weird. This looks okay, except that we don't actually have this I2C number set. For now, let's just pick the first one. we're just trying to get something working in the next 15 minutes, let's just say 0. Wha-bam. It's a good way to, it's good to only do pieces at a time. And then the config, do that. And I think we do want to save 0. I want to save what I2C number we're doing. So we actually want to do self this. Anybody else had a chance to try the ESP32S2 CircuitPython? I think Brandon was the one that got the green LED working. Okay. That looks good. Probe. Let's do this. Because probe is what scan uses. So let's pull up the description of the API again. So what we're going to do is we're going to do an empty write, I think. And so we're just going to want to copy this I2C command link. I wonder if that actually does an allocation. That's not where I want it. Link create. And then, oh, I'm going to pull the reference up on the left, or on the right off screen here. Over the chats, just because I'm copying it. Command create. So we're going to start off by doing a start bit. We're going to do I2C master write byte. I am missing. Nice. P-Boy says ESP32S2 board expected delivery by Tuesday, May 26th. So you have it for next week. That's awesome. I also ordered, since I'm getting distracted, DigiKey also has the other dev board. I can't remember what it's called, but we can look at my orders. And it's fine, you can't see it. Oh, this may have my address though. Let me move it off. Click. So the Sala is one of the 2 ESP dev boards. Kaluga is the other one from Espressif. And it also has the native USB hooked up, I believe. And it has this screen. So they had 3 in stock when I looked yesterday. Can I click that for a bigger version? Yeah. So let's see. Yeah, there's 2 USB plugs here. D-Flower says M1. I don't know what you mean by M1. Yeah, the Calis. Yep. So I ordered one of these because DigiKey had it, which is cool. So I got one on the way. I think it comes on Saturday. So that's super exciting. And so next week we should be able to play with that as well. I bet it has I2C stuff on it too, actually, which is cool. Okay, yeah, autocorrect. Yeah, I know. Autocorrect is never right for me. Go back to my reference. Mark says, I think Unexpected Maker has one. Has one what? A dev board? He's tried to send it to me in the mail. It's just like... So yeah, Unexpected Maker, I think if you're watching me still, I would like that pinout. I'd love to make a breakout that matches your feather. Oh, yeah, D-Flower says, sorry, I thought you were talking about the one without the PSRAM. No, I actually have both of those already. DigiKey had them as well. They look exactly the same, except for the module. But I do have both a rover and a room. I have one of each. PSRAM is something we have to add. We'll add it later. Okay, we want to get probe working. I'm letting myself get distracted. Let's get scanning working at least, and then I'll figure out how to wire something up. That's why I brought my whole thing of dead boards. Okay, so we're gonna do write byte, and we're gonna give it command. We're gonna give it address. We're gonna give it ACK. And then we're actually, the next thing is a write, but we don't care about that. So I2C master stop command. And then we're going to do I2C master command begin the self I2C number, the command, and wait, whatever that is. I will scroll down and look. Okay, so let me see if I can't. Bruce says, back in the car, out to UPS and back. All right, let's scroll down where we can see the full. Oh yeah, we haven't even, I guess we set the frequency in the config. These are good docs. Good job, Espressif. We're not using the ISR. You don't need to set the pins. All right, I2C command handle is the type for command. Click it back. And then after we're finishing sending commands, we need to call delete to release and return the resources. Okay. We can do that. And we're blocking. Like we queue for the command I2C to generate a start signal. Write 1 byte to the I2C bus. Bool is ACK enable. Oh. It enables the ACK check for master. True? Because that's the way that we know whether there's a device on the bus. Is that if it acknowledges this first write byte, which includes the address, then we know it's there. So Oh, so this is how you write more than 1 byte. We don't need to do that now, but we'll basically do the same process that we did here, just further down. Read byte we're not going to do. Read we're not going to do. We're going to queue up a stop, and then we're going to do begin. And this ESP fail is the thing that we're going to want to look out for. So this sends the key commands. The task will block until all the commands have been sent out. And we're not going to worry about multi-threading right now. Maximum ticks to wait. We could potentially wait a while. Ticks are pretty slow. I think they're 100 per second. And usually as a I2C master, you don't have to worry about it because like you're setting the clock rate, so we don't actually do timeout stuff externally. Okay, but we do want the ESP, what is it? Result? ESP, we call that result. We do have to be a little wary of blocking. I'm not going to worry about it now, but if we block here, we potentially block all of this background stuff that CircuitPython does. We're not good at, we haven't moved that stuff to FreeRTOS and handling it separately, which maybe we'll want to do, but for now, we don't care. The USB will work just fine because we did move that away. So let's check ESP fail. ESP error T, okay. Result, and then if result is anything but okay, we don't actually have to check fail, because if any of the other things happen, we're not going to want to say the device is there. Actually, that's not equal. It should be equals equals. So the device is there if we successfully did it, which is exactly what the version for this handy was checking too. Okay, so that is that. Let's see if it compiles. No worries, unexpected maker. I think a lot of parents are excited for their kids to go back to school. We've been binging Bon Appetit's YouTube channel, and one of the folks there has 2 kids at home that, or a lot of them have kids at home who have been on their videos, which has been entertaining. But yeah, when you have a chance, Unexpected Maker, send me your pinouts and I'll make, one thing I want to do this weekend is that, is the Sala breakout board to have a feather footprint so I can test with feathers. Most feathers are I2C, so that would make it super easy to test stuff. Okay, this is complaining about the FreeRTOS ring buffer. And that's probably because we haven't included the appropriate directory that includes that file. Oh, it's not I. Oh, I think it's just dash name. Haha. Oh, it's in components ESP ring buff include. Haha. Bruce says, same here for Bon Appetit. So much fun watching them at home. Yeah, if folks haven't seen it, they get like 1 million views, so you probably have seen it, and I'm just late to the party. But the thing that got me hooked into it is that on Hulu, they had the versions. There's a particular type of show they do, which is they blind somebody. Bye, Unexpected Maker. Thanks for dropping by. They blind one of the guys, and he like uses his fingers to eat food, and then has 2 days to replicate the dish based on what he tasted and what he touched, but he can't look at it until the end, which is entertaining. Okay, make. Where are my make files? I was thinking I was going to do Ninja stuff this weekend, but I have this other idea that I think I really want to pursue that is not Adafruit related at all. But I was walking around today and noticed all the businesses that are like closed up or takeout. And I thought it would be great to have a website you could go to and just find all of the things you could buy from all the businesses locally online. So I might do that. Basically scrape a bunch of independent online stores and create one storefront or like meta storefront. I wouldn't do any of the like actual payment stuff. But it would be just a way to like basically search across everything that's local. That has nothing to do with the ESP32S2, but that is the idea that I stumbled across earlier, and I think I want to spend some time this weekend on. I already bought the domains. Of course, that's the first thing I do for a new idea. Domains are so cheap. All right, I2C port T is not there. Oh, I can't see the Discord chat. Let me click that. Bruce says, nice being late to the party. Now I have a massive backlog to watch. Of today's or like, oh, of Bon Appetit. Yeah. And yeah, Mr. Certainly says, wait, thunder in Seattle? Maybe not. Something loud. Like there's some rain, but it's not a ton of rain. It might have just been somebody nearby, like knocking something over. Okay, so it's in I2C types. I think I'm debating. Ivan suggested the includes being relative to like the include for the ESP IDF, but I think I actually want for CircuitPython to just do it relative to the ports directory. I think that makes it like, so here we have just driver I2C. I think doing the longer form is actually much clearer where it's coming from. Oops. Dinobot made. Charles said create a wish list. Yeah, for like buying stuff locally. I was just looking at the farmer's market, and the farmer's market has this website that's like super long. Oh, that didn't fix it. Fancy routing. Nice. Huh. That's a little weird to me. The I2C, I'm including it in the right file. Oh, okay. This is awesome. Freaks says, I was just out walking the dog in North Seattle and there's definitely thunder. So I'm not crazy. I'm like in Ballard, so I'm near North Seattle. So yeah, I would have heard it too. Glad you're watching. You can confirm the weather outside when I have headphones on. Bruce says that would be a great way to support local businesses even post-COVID. So many times I find a place that's always been there, but never knew about it. Yeah. Yeah, that's the idea, is like, it's basically finding all the separate web stores for all the businesses around you, and then aggregating the search into one place and the browsability in one place. I'm going to play around with it this weekend. Talking about weather, Bruce says it's rather cold and cloudy here, sort of trying to rain in north of Vancouver, just like 2 or 3 hours north of me. Yeah, there's two Bruces talking to me. David pulls up the forecast for the Seattle area, saying, with just a bit of daytime heating, heavier showers may contain some small hail. Cannot rule out an isolated rumble of thunder or two, but not expecting too much in that sense. David says, oh, and you know what Google Maps has available? I don't know what you're referring to there, but please let me know. Mark in Discord is working on his weather station housing. I think it'd be cool to have a weather station. Get distracted. Is it Friday yet? No, it's not. It's Thursday. It is my Friday, though. So I included this, and that's where I thought it was. Yeah. Yeah, David says, what part of Google did you work at? Yeah, I thought it was Maps. Yes, it was Maps. And now my wife works on Maps. Made for a weird holiday party. Oh, okay. So this is in Common Hal I2CH. That's my problem. So I need to move this from here to here. All right, and then we got to figure out where this semaphore comes from. And that's in the same, we need to put the include in the same file. And yes, I realize there's much easier ways to do this. I'm just like so old school in some of my ways of finding stuff. I feel like I do some things that are not super efficient, but the reason to do them is they apply in a lot of cases. They may not be ideal for this particular case, but they are good overall. And I see you, Mark, and I'll reply to you. Mark says, should I remove the ground planes on my board under the part where the Wi-Fi antenna is on the Sala? I would, yes. Although it'll be sticking pretty far away, so it's probably not a problem. But I think generally it's not good to have ground planes near antennas. I'll probably do that on mine if I'm able to, even though it's going to be like a pin header's worth away. Looking for a type def. There's a pound define. If only there was software that on a computer that would do this. Which there totally is, and I'm not using. Mark says, 2 Bruces and 2 Marks. We need more diversity. It's true. Diversity is a good thing. I realize I'm over time, but I want to ideally get this to work before we finish up. I don't see it. Do you all know what I have to include for this semaphore handle? I don't even know where I got this. Where did I get this? Bruce says, should I do a pull and build? I haven't pushed this stuff yet. So you won't have the BusIO stuff, but you could do the other stuff. Did I scroll right by it? Or does it not actually exist? Oh, here it is. FreeRTOS semaphore. It's actually a Q handle. Let's see if that works. Oops. That is not what I wanted. And the flash is not going to work because it's not plugged in. Doesn't matter, it didn't compile. Mode is undeclared. I think that's because it needs to be dot mode. These all need to be dot for the initializer. I think semicolon is right. Nope. It's not right. Oh, and I removed haslock. I think I do need that still. To know if we have the lock. See how we're doing. Ooh, getting close. And is it just is it supposed to be empty or is it commas? Syntax is the worst. Maybe commas. It'll still complain if it's commas. Yep, it's commas. I think. Let's try it. This riveting programming. What board I have. I'm not gonna do a stemma one because I don't have the thing. There's so many to choose from. How about what's the theme? Our theme is weather. Let's pick a temperature sensor. We're just gonna scan for it, so it doesn't actually matter. Gas sensor. Too many to choose from. Here we go. This is what we'll do. We'll do humidity sensor. SHT31D. All right, and sorry in advance for the fact that I don't have the overhead working. P-Boy says, okay, if you can't hear us, what's playing in the headphones? Nothing is playing in the headphones. Just my voice. I do tend to hum, though. I might have been throwing you off with that. Okay. Let's switch pins. And I'm going to make black to ground. And a 3.3 volts ground. All of our breakouts have pull-ups on them, so I shouldn't have to do that. I should be able to just connect it up. Oh, you know what? I may not have enough female headers. I need to make this breakout. I had more wires. Your voice is inside your headphones. Yes, it is. It's in both my head and my headphones. Too bad I grabbed the wrong thing. All I have is male wires. It's most unfortunate. Here we go. I can use this. I've got this thing. I don't know if you can see it. It's got a potentiometer on the end with 3 female things. Okay, perfect. So I'm going to plug that into 34, 35, and 36 arbitrarily. And I'm going to make 34 clock and 35 data. And now I gotta, oh, did it show up as a drive? Yes, it did. That's good. It's alive. And let's switch this from the debug to here. And I'll double click code. Oh, that is not good. That is not right. For sure. There might be a bug or two with this port. We're gonna... That explains why it's saying invalid syntax. You know, this is not the first time this has happened to me. This happened to me before. So this is definitely a bug I'm going to have to look into probably pretty soon. But for now, I'm just going to delete it and import BusIO, import board, and see if I can make a bus. BusIO I2C. And I said board IO 34 was clock and board IO 35 was data. And then we should just print bus.scan, I think. Not all characters are representable in hexadecimal, falling back to UTF-8. Thank you. That is the right answer. and it's running, but something bad may have happened because the auto reset's not working anymore. Ooh, that's not good. Didn't work. Okay, so I'm turning off the data cable. So it's been ejected, and I'm gonna just control C this, and I'm just gonna make it again. What I want to do is I want to get, I want to save it one more time, although it, yeah, okay. So now we need to add debug logging. And once again, we're going over time. Hopefully that's okay, but I had a goal. I'm gonna get the goal. So let's snag the log stuff. And I wonder why it's failing. I don't know it off the top of my head. Do I need to try lock on scan? Maybe. If it was working, yes, I think. But, yeah, maybe. It's certainly not supposed to. I think it's const care star tag equals Python I2C. And let's just look for tag. Good idea. Whoa. That's enough. Except I want the early ones. I don't want it in. Trying to limit it because I want to copy how I've done it here. So static const care star tag. And let's just see how far we get. So create I2C. And then create I2C done. And let's follow Summersoft's lead and check the lock stuff. Unless that got dropped. Maybe not. Docs don't have it in the example blurb. I'm probably thinking about I2C device. Either that or the docs are wrong, which is also possible. Okay, let's go with that. And see what happens. See how far we get. Printf debugging for the win. Oh, okay. So we didn't even make it out of the constructor. Y'all can see that mostly. Okay, so the question is how far do we get in the constructor? And why are we getting like super fatal error, which is kind of surprising. Let's do here. See if we get that far. Ooh, this will be exciting. I do want to make a board though. I feel like doing a board layout. If my voice wasn't bothering me, I'd stream that too. Okay, so we didn't even get that far. Now, do we get even that far, or do we have a problem with this semaphore I'm making? That's so weird. If so, we can just not do that. I can do it later. Okay, so it is after the lock. But is it this? Which is kind of weird. Are we setting I squared C num? Yes, we're setting it to 0. Should be okay. I'm surprised it's dying so completely. Like, as param config, like, does argument checking, and it returns an error code. So it didn't get that far. Is this not right? Am I not allowed to do that? Load prohibited. If I was using IDF monitor, it would give me a backtrace. I mean, I know where I am, but Lasai. I wonder if SDA and SCL pins are wrong. That could be it. Let's print that stuff out. Let's see, SCL %P for pointer, SDA, P for pointer, and then self. Oh, these are totally wrong, because I don't set them till here. That seems suspect. Okay, so printf debugging for the win, right? Dereferencing null, like a dummy. Assuming it's null. There we go. Got a little farther. And now we're just sitting. Why is that? It shouldn't get stuck in param config. Oh, you know, maybe we raised an exception. Let's do that. Error %D result. That's probably what happened. Wouldn't make sense that it would like spin forever. Maybe we do want to print these off too. We won't do the pointer though. They should be the numbers we expect. We're gonna have to compile it again, but that's okay. Error 258. What is that? It's a high number. Let's take a look at the implementation. If I can remember where it is. I don't need the Pi folder open. ESP IDF. Driver. I squared C. param config. Set pin return. Maybe pull up enable is not correct. Like ESP okay here. The only other thing is the return code from set pin. So let's find set pin. What if it did the detection for us? Here it is. Lots of checks, which might do returns, which is likely this. Pull up enable versus pull up disable. I'm sending true or false, which is probably not right. I want to disable on both. So let's give this instead. And let's try it again. It could be a frequency thing, actually. Although it's in pin. Ooh. It's really unhappy again. Oh, probably because we're printing out the pin numbers before we set them again. We're doing the same thing we did last time. Silly. Dot, dot, dot. Did y'all just like get off? I went too long. People dropped off. Hour 3. All right, SCL35, SDA34, that's right. And then error 258. Still, even though we changed these to pull up disables. This says ESP okay. I don't know what this I2C check does. Whoa. I rewrapped everything. How are we getting a 258 out of that? Look, it's even sending in error strings for each of these things, but we're not seeing any of the error strings. So they must be turned off. What does I2C check do? I2C tag. It prints stuff off and then returns with the return code. Ooh. That's good. Where do the return codes come from? Let's go back. Set pin. Ah, error, invalid arg. It returns the same thing over and over again. That's so helpful. But it's not printing it out. Invalid arg must be 258. And I'm probably missing the way to turn it on. Let's do define. All right, I'm about to give up on this. That looks suspect. 258. Okay, so it is an invalid arg. And the string, invalid arg. Yes, exactly. Is valid output GPIO. IO number is less than 0. Okay, so that's fine. Or is disable. So these two are right. These two are right. I2C number? I mean, we're setting it to 0, which should be fine. That's it. I2C is cut from CircuitPython. Yeah, exactly, P-boy. It's too hard. We're not going to do it. But these error strings, it would be nice to figure out how to get these error strings. ESP log E. It seems like it should be on. But it's not. This I2C pin does not support internal pull-up. Well, what if we hand 1 in? What if we just say 1? I2C number 1. Maybe it's 1 based? Let's just try it. We're so close. Even though I still haven't found wires. Uh-oh. Oh, no, I did. Come on. Don't crash. Come on. Error 258 still. And it's not printing out what it should be printing out. Like, why is that? I2C tag. It's error level warning. Huh. TigerByte is typing. Hopefully has the answer to my problem. Oh, this is interesting. 1.1 mode master. Clear bus. Is there a reason those pins wouldn't work? Should we try some other pins? And why aren't they showing up on the serial output? That's the bummer. Maybe I haven't turned it on or something. This is what I get for starting late. Ivan's already asleep. Can't rescue me. Did you set the speed? I didn't. Did I? Yes, I did. It's right here. But yeah, maybe that's my problem? No, because... Well, let's see. What does param config do? Is param config checking the speed? I could be hitting these invalid args. But it's only checking the I2C number. Break out the logic analyzer or try an IDF example. I'm 2.5 hours in. I'm about... Should I call it? Is there anything else I should try? I think I'm going to call it because my brain's stopping. Bummer. Well, I'll probably figure this out right after I stop streaming. But it's been 2.5 hours. I appreciate all the support. And of course, we should remind everyone that programming is not always accomplishing the thing you're going for right at the end. Although it probably will bother me. We'll see. But it's 5:30 here, and I should wrap it up. So thank you all for joining my stream. I hope this was insightful. I spent a lot of time talking about all the different bus types, which I hope was super helpful. It's something that's been stewing in my brain a while. I was thinking about doing a talk on it, but I just did. And hopefully it was helpful. Sorry that there wasn't great visuals to go along with the stuff that I was talking about. If you have questions, feel free to reach out to me. You can do that. I'm Tannewt on Twitter, TANNEWT. Follow me there. I've been posting about when I'm streaming. This is an exceptional time. I'm normally 2 p.m. on Fridays, but I'm taking tomorrow off, so I'm on a different day. You can also get a hold of me on the Adafruit Discord server, which is the URL adafru.it/discord. And I'll just switch to the camera while I wrap up. I'm Tanut on the Adafruit Discord server, so you can mention me there and I'll see it. I do try to avoid it or ignore it on the weekends. But if it's something quick, I might be able to hop on and help. If you're interested in this like idea I briefly talked about that's totally unrelated about supporting local businesses by aggregating their disparate web shops together into like a portal or like a meta shop, let me know. I think I'm going to do some research on that. And otherwise, try the ESP32S2 stuff out. Keep an eye on the PR for the digitalio as well. Support Adafruit. Order Adafruit stuff either from DigiKey or other places, or from Adafruit directly. They are shipping out now, albeit potentially slowly because they're still ramping up in terms of having folks on site and prioritizing COVID-19 related orders. I think that's about it. I2C will be super exciting to figure out, get going. And once I figure out kind of the process here with using the IDF, it should make SPI and the UART stuff go quicker too. So it's a start. I'm taking Monday off as well. So if you do check out the CircuitPython weekly stream, remember that'll be on Tuesday as well because of this US holiday weekend. And if you don't know what that is, I highly recommend reaching out and asking about it. It's basically a community meeting we run on our Discord server for everybody that's doing CircuitPython related stuff. So we'd love to have you in that. We are starting to do it with video as well. So we might actually do that as like an unlisted stream to YouTube for those folks who are just lurking, because we can only fit 25 in the Discord channel if we have video on. So I'll have to remember that for Tuesday. And I think that's it. I feel like I'm missing something. It usually takes me a while. But yeah, thank you all. I appreciate you hanging out with me and watching these videos. If you're watching this later, you made it to the end. Congrats, which is surprising. If you have comments or questions, find me on Discord, find me on Twitter, or drop a link or a note in the comments. I do look at the comments, or I try to at least once. But it's better to just like at me on Twitter or Discord, because then it'll tell me to look. Obviously, it's on the Adafruit YouTube channel, which I don't get emails about when comments happen, because lots of comments happen. And I'm rambling. Have a great weekend, everybody. Thanks for hanging out, and I'll see you next week.